Hey everyone, welcome back to Linear Algebra. This will be lecture 17 of the course. And in this section, we're going to discuss basis and dimension, two very interesting concepts that follow directly from our previous discussion of span and linear combinations. So let's go ahead and jump into it. So we'll call this section 4.5. Basis and dimension. Okay, so let's go ahead and kind of set the stage here a little bit. Let's assume that we have a set S in a vector space V. Okay, so assume S is a set in V, a vector space. Okay, so S is not a subspace, it's just a set. Okay, let's assume that V, a vector, is in the vector space V. Okay. Then there are two questions that are pertinent to this lecture. So two questions. Okay, the first one is this. The first question is there a linear combination of vectors in S, okay, that is equal to this vector V? Okay, so you've got a vector V in the vector space, you've got a bunch of vectors in this set S. Is it possible to write V as a linear combination of the vectors in S? Okay, this is kind of like an existence question. Okay, it's an existence question. The second question we can ask is a question about uniqueness. So if there is a linear combination of vectors in S that is equal to V, is it unique? So if so, is this the only such linear combination? Right? Meaning, can you do it in lots of different ways? Is there one combination for V from the vectors in S, or are there many? Okay, and so this is a uniqueness question. Uniqueness. Okay. Now the existence question, question 1, is really just the question of whether or not this vector V happens to be in the span of the set S. Right? So the existence question is really just just the question of whether V is in the span of S. The vector V is in the span of S. So we talked about span last time, right? That just, to be in the span of S simply means that you could be written as a linear combination of the vectors in S. Okay? So that's the existence question, really. The uniqueness question boils down to something as well. So the uniqueness question. The uniqueness question is equivalent essentially to asking whether S is linearly independent or not. So the uniqueness question is, equivalent to asking whether S is linearly independent or not. Right? If it's linear, we saw this previously, if S is linearly independent, then all of the linear combinations you can spin up in there are unique. If S is not linearly independent, meaning that one or more vectors in S can be written as linear combinations of the other vectors in S, then the linear combinations are not going to be unique. Okay? So it kind of boils down to these two ideas here. And so in this section, we want to combine the existence idea with the uniqueness idea, and when we bring those two concepts together, what we end up with is this idea of a basis. Okay, so when we bring existence and uniqueness together, we get to the idea of a basis. Okay, and let's go ahead and define a basis quick, and I think you'll see exactly what I'm talking about here. So we'll let V be a vector space. Okay, so we got a vector space V as per usual, and we're going to let B be a subset of V. Okay, it's a subset of V. Then B is a basis for V if and only if both of the following are true. Right, and so the two things are that B has to span V. Right, if B is a basis for V, then B is going to span V, meaning that any vector in V can be written as a linear combination of the elements of B. Right? So B spans V, and the second one, so that's the that's the existence, and then the uniqueness is that B is linearly independent. Okay, so those two ideas come together, and when you have both, then you're dealing with what is called a basis. Okay, so that's what we mean by a basis. Okay, all right, very good. Let's go ahead and let's do an example. Let's get some vectors out and talk about this specifically. So let's consider this set. Okay, and so we'll go 1, 2, 1, and then 2, 3, 1, and negative 2, 2, negative 3. So this is obviously a subset of R3. Okay. And the question is this a basis for R3? So is B a basis for R3? Right? So we need to, in order to determine whether that's the case, we need to show two things. First, that the span of B is equal to R3. And second, B is linearly independent. Okay, so we need to show those two things. And if we can do that, if we can show those two things, then B must be a basis for this vector space R3. Okay, now to show that, we'll start with the first one. To show that B spans R3, we can use a test matrix. So let's write this down. To show that B spans R3, use a test matrix. There's different ways to do it. The most expedient way to do it most of the time is to use a test matrix, and we're going to insert the elements of B into the rows of the test matrix. So we want to put the elements of B into the rows. Important, right? Right, because what we're doing is we're taking B and we're creating a row space from B, right? And we can then use row reduction to determine, we can row reduce that matrix, and that'll give us insight into what the span is. Okay, so we'll take these and just plug them into a matrix as the rows. So the first row will be 1, 2, 1. The second row is 2, 3, 1. The third row is negative 2, 2, negative 3. We'll plug that in. That's a matrix. Then just do some row reduction. on this, and I'll let you, obviously pause the video, take a second, make sure you can do that. But when you do that, what you'll find is that you get this. Right, you get this whole matrix row reduces to this identity matrix, this 3 by 3 identity matrix. And so we can read off what the span is here. So the span of B is going to be equal to the set A times 1, 0, 0 plus B times 0, 1, 0 plus C times 0, 0, 1. Right, obviously A, B, C are real numbers. Right, and so from this, it's clear that this is going to be equal to R3. Okay, so and clearly, therefore, the span of B equals R3. We get them all. There's no vector that can escape this. Right, there's no vector in R3 that can escape the span of B. Okay, so we have shown that B spans R3. So we're halfway there. The other half is to show that B is linearly independent. Right, so to show that B is linearly independent, we can use a test matrix for that as well. This time, however, we're going to plug the elements of B into the columns of the test matrix. So we're going to put the elements of B into the columns. Right? So instead we get 1, 2, 1 as the column, 2, 3, 1, and then negative 2, 2, negative 3. Right? And then when we row reduce that, what do we get? Well, 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, and so from a previous lecture when we discussed linear independence, we saw that if a matrix can be row reduced and its row reduced echelon form has a pivot for every column, then all of the columns of that matrix are linearly independent. Right, and that's exactly what we're trying to show here. We're trying to show that these three columns, i.e. these three elements of B, are linearly independent. Okay, and so B is a linearly independent set. Okay, and so that, combined with the fact that it spans the vector space R3, means that it's a basis for R3. So both of those things together imply that B is a basis for R3. It spans R3 and it's linearly independent, so it's a basis for R3. By definition, that's the definition. Okay. All right. Very good. Let's look at a couple more examples. We want to make sure we develop good intuition about basis. Let's take another example. So let's, any vector space, if you think of a vector space Rn, right, there's always going to be a basis that you can easily identify for Rn, right? So the vector space Rn has E1, E2, ... En as a basis. Right, so these E1, E2 through En, these are the standard unit direction vectors. Right, so 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, etc. Right, so these are just the unit direction vectors. Right, and so this basis is called the standard basis for Rn. Right, it's the basis you can always rely on. It's always there. It's always easy to find, and it's very, very obvious. Right, it's clear. For example, with R3, so clearly 1, 0, 0, 0, 1, 0, 0, 0, 1 spans R3. Right, we just saw that, right? Any vector can be written as A times this one plus B times that one plus C times that one. There's no vector in R3 that you can't write using these three as a linear combination. And obviously they're linearly independent, right? None of these vectors can be written as a linear combination of the other two, right? So this spans R3 and is linearly independent. Those two together mean that this is a basis for R3. And you could extend this to any n vector, right? A collection of n vectors will always span a collection of n linearly independent n vectors will always span Rn. In this case, a collection of three vectors that are linearly independent spans R3. Okay, and this again is called the standard basis. We'll use this a lot in the coming lectures, the standard basis. Okay, what about with a matrix, a matrix vector space? Well, is there a standard basis for something like M32? So if we consider M32, the 3x2 matrices. Right. Well, this is a vector space, right? You can use scalar multiplication and matrix addition. We have closure there, right? And then all of the other things are met as well. So this is a vector space. What's a basis for this vector space? Well, the standard basis for M32. So the standard basis is, and this may or may not be obvious, but 1, 0, 0, 0, 0, 0. You're going to have 6 of them, right? 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, sorry, too many 0 1s. Right, so you can see what we're doing here, right? Basically just, we need a matrix that's all zeros except for one entry. And you just iterate through all of those entries and you get the standard basis for M32. So this is a 1 here. Okay, and I don't have to write it out, but you can easily imagine that if I take A times this plus B times this plus C times that, D times that, E times that, F times that, then no matrix in M32 can escape being written as a linear combination of that structure. And further, these are all linearly independent. There's no way to write, for example, this guy here as a combination, linear combination of the others, right? The 1 up here can't be generated using scalar multiplication and addition. You can't write this 1 in terms of these other entries because they're all 0, right? So linearly independent. Okay. Very good. Here's another example. Just one more quick. What about polynomials, the other nice vector space that we've discussed? So we define 1x, x squared, x cubed to be the standard basis for P3. Okay. Right. I mean, so any third degree or less vector, or sorry, any third degree or less polynomial can be written as a linear combination of these three. And also, none of these vectors can be expressed as a linear combination of the other three, right? So there's no way for me to write x squared equals some linear combination of 1x and x cubed. Can't do it. Try to do it. See if you can figure out a way to do it. It can't be done. These are linearly independent, and they are sufficient to describe through through normal polynomial addition and scalar multiplication any vector or any polynomial in P3. Okay, so similarly, or generally, 1x x squared dot 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 xn is a standard basis for P sub n. Okay, so just in general. Okay, excellent. All right. Okay, so in this section we're kind of mostly focused on the idea of finite bases, and we've got a handful of theorems here that we want to prove. Let's see. So we want to talk through one. Let me think here. There's two. Yeah, so there's really, I guess there's two sort of, I guess you could call them lemmas. I tend to think of them as full-blown theorems, but we've got two theorems coming up. I'm going to write them as lemmas. Two lemmas that can be used to prove a big theorem of linear algebra. Okay, and so just in case you're not clear, a lemma is kind of like a little theorem. You can think of it as a little theorem, which frequently a lemma will emerge when you're trying to prove a big theorem. You might prove a case or a portion of the proof. You might be able to derive a portion of the big theorem's proof and write it as a separate theorem to be proven separately. And so a lemma is kind of like a little theorem that it usually is written to simplify the proof of a big theorem, right? And so we have two kind of lemmas to talk through, and then a big theorem from linear algebra. Now, the first lemma, the only reason I hesitate to call it a lemma is because it does have a pretty challenging proof. The theorem is also quite profound, so I'm almost inclined to just call these all theorems, but technically speaking, most textbooks will refer to these as lemmas. So let's go ahead and talk the first one through. And this first one we're not going to prove in this course simply because it would take about 45 minutes. I think the proof is not beyond the lecture or beyond the level of somebody taking linear algebra for the first time. But it's just in the interest of time, we're probably not going to prove it. So let's talk it through. Let's write it out and then see some examples, make sure we understand what this is saying. So let's let V be a vector space. Well, let V be a vector space spanned by the n element set S, and let's just call the vectors in there v1 dot 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 vn. Okay, so let V be a vector space spanned by the n element set S equal to the v1 through vn, and let T equal the set w1 dot 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 wn be a set of linearly independent vectors in V. Okay, so I've got these two sets, and we haven't written the punchline yet. Let's make sure we understand the setup here. So V is a vector space, and you've got this set S which spans V, right? So S has n elements and it spans V. You got separately you have the set T, which also has n elements, potentially totally different from the elements of S, which is linearly independent and comprises obviously of vectors from V. Okay, so S spans V. T, we're not saying it spans V, we're saying it's linearly independent. They both are the same size. S and T have the same number of vectors. Okay, so then the punchline here is that the span of T is equal to V, and T is a basis. for V. Okay. So, I mean, really the only thing here that is kind of the jump here is that T somehow is a span, the span of T is somehow equal to V automatically by virtue of its size, seemingly, and the fact that it's linear, well, just by virtue of its size, and the fact that it's linearly independent. And then, of course, the fact that it's linearly independent and that it spans V automatically makes it a basis for V. That's by just the definition. Okay, so this is the interesting part here, right? The fact that T is going to span V kind of automatically, right? So what is this saying? Let's go through this one more time. This theorem basically says that if a vector space has a spanning set of size n, in this case S, and I have a second set of n linearly independent vectors, then the second set is automatically a basis. Okay, so let me write that down. So if V has a spanning set of size n, okay, all right, so V has a spanning set of size n, and if I have a second set of n linearly independent vectors, right, so these two items, then the second set is a basis for V. Okay, so from the first set we get, we're told that it spans and it has size n. So what that basically means to us is that we now have a number of vectors required to span the set, right? It could be fewer than n, but it can't be more than n, right? I don't need more than n vectors to span V. I need no more than n, right? And secondarily, if I have n linearly independent vectors, then that means I can't throw any of those vectors out and still span V, right? So I know that my linearly independent set, I can get up to n vectors, and it takes no more than n vectors to span V, so that those two pieces automatically together imply that this second set is automatically a basis for V by virtue of its size and the fact that it's linearly independent. Okay. Now, as I say, the proof of this theorem is not in and of itself beyond the scope of the course. It is rather long. It's a rather long proof, at least all the ones I've ever seen of it can be rather lengthy, but none of the moves in it are outside of the scope of the course. So I think if you go on the internet and you start you type this into any search window, you'll be able to find an example of this proof pretty quickly, right? And you can walk through it. It does have some very clever moves, and I do recommend you take a look at it, but just in the interest of time, we're not gonna prove it here. But let's see an example of this. Let's see an example of how this is super useful. So let's let S equal the set E1, E2, E3, E4. Okay, and this is obviously a subset of R4. Right, and we know this is the standard basis for R4, so it clearly spans R4. So clearly S spans R4, right? So what we're doing right now is we're creating we're recreating the conditions of the theorem, right? So this is the set that we know is the spanning set, right? So the spanning set S here has 4 elements, and that's kind of the most important part. Now consider also the set T. Right, let's say T is equal to 1, -1, 1, and 2. and 2, 1, 8, 13, and 3, negative 6, negative 5, negative 5, and negative 4, 10, negative 2, 7. Right, so you've got this set of 4 vectors. Right, now, what the previous theorem says is that because a spanning set requires no more than 4 vectors, if I can find another set of 4 vectors that happen to be linearly independent, then that set is automatically a spanning set, or automatically a basis. Okay, so that's what we see here. So we've got this, it clearly spans R4. And then I've got 4 other vectors here in this set T. Now what I want to show is that this is linearly independent, and if that's the case, then this is a basis for R4, these 4 vectors. So is T linearly independent? That's the question. Well, we can test this quickly, right? The kind of the wind-up of the first, the first example we saw showed us how to quickly test this. We just plug these in as columns into a test matrix, row reduce it, and see what the reduced row echelon form of the matrix looks like. So 1, negative 1, 1, 2, 2, 1, 8, 13, 3, negative 6, negative 5, negative 5, negative 4, 10, negative 2, 7. Put that in there, and then do some row reduction. And you'll see you get 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Okay, so you get the identity matrix. And so by the previous theorem, right, so what does this tell us? This tells us that these 4 vectors are linearly independent. So T is linearly independent. Well, the previous theorem says automatically then that T is a basis. And it's a basis specifically for R4. Okay, very nice. Right, so that's the first lemma. It's kind of, what it's doing is tying together the idea of a size of a spanning set and the size of a linearly independent set, kind of bringing those two concepts together, right? If you know the size of a spanning set and you have a linearly independent set that is the same size, then that other set is automatically a basis. Okay, very good. So the next lemma / theorem is going to expand on this a little bit, and it's going to show, what we're going to show is that the size of a linearly independent set can never be larger than the size of a spanning set, so long as the spanning set is finite, of course. So let's take a look at this. All right, so we're getting very close to the big theorem from this section. All right, so here's what this one says. Okay, so let's let S and T be subsets of a vector space V. Let S and T be subsets of a vector space V. And I guess we'll say such that S spans V. Okay. S is finite. Okay. And T is linearly independent. Okay. So here's the wind-up. Here's the assumptions. If S and T are subsets of a vector space V, and S is spans V as a spanning set, S is finite, and the set T is linearly independent, okay, then what's the conclusion? Then T is also finite, right? The set T is also finite, and in fact, the size of T, the number of vectors in T, is less than or equal to the number of vectors in the spanning set S. Okay, so just as we led with, this shows that this theorem shows that the size of a linearly independent set cannot be larger than the size of a spanning set. Okay, in the case of the spanning set being finite. Okay, this one we can prove. This one will prove. It's not too long. It'll take only a couple minutes here. So, if S is empty, so first of all, let's kind of settle this. We're done. Okay, so if S is empty, then we're done. So let's assume that S is non-empty. Assume the S contains at least one element. Okay, so the size of S is greater than or equal to 1. And what we're going to do is we're going to generate a contradiction by assuming something up front that is false. Right? So we'll write a proof by contradiction. So assume that S is greater than or equal to 1, and we'll provide a proof by contradiction. Okay. All right, so we'll assume that S is greater than or equal to 1. We'll assume the size of T is infinite, or the size of T is less than infinite. We don't care, it's finite or infinite. But what we are going to, here's where the contradictory issue is going to arise from. We're going to assume that the size of T is greater than the size of S, which we'll call n. Right, so our theorem says that the size of T, the linearly independent set, will be less than or equal to S. But what we're going to assume is that, no, we're going to assume that it's larger. And we'll see that we can easily generate a contradiction when we do that. Okay, so if T is greater than S, the size of T is greater than S, then there's some subset of T and the subset we'll denote as just W1, Wn, Wn plus 1. This is a subset of T, right? Which can, as we've written, you can see it contains n plus 1 vectors. Okay, so T is linearly independent. It's got n plus 1 vectors. Okay, we assume it's linearly independent, and if the size of S is n, then there's some subset of T that has n plus 1 vectors at least. Right? It's larger, right? It's got to have at least one more vector. And this is linearly independent. Okay, so we assume, since T, we assume that T is linearly independent, so because of that, any subset is also linearly independent. So since T is linearly independent by assumption, any subset is as well. Well, that was a theorem from the last section, I believe, from the linear independence section. We discussed that. So what does that imply? Well, that just implies that W1 dot 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 Wn, Wn plus 1, and also the set W1 dot 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 Wn are linearly independent. Yeah, so I've got these two sets. They're both linearly independent. Okay. The set S spans V, right? That's an assumption. We've assumed that S spans V and that the size of S is equal to n, right? So, but S spans V and the size of S is equal to n. So, thinking back to just the theorem that we just finished with, our previous theorem, the one we just finished, is going to imply something. What does it imply? Our previous theorem implies that W1 dot 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 Wn is a basis for V. Right? Does everybody see that? Right? S is a spanning set. S spans V. It's got n elements. This subset of T, W1 through Wn, also has n elements and is linearly independent, so it's automatically a basis for V. Okay. Okay, so we're getting things are starting to coil up here a little bit. You might be able to suspect how we're about to run into some trouble. Okay, so what comes next? Well, Wn plus 1, the n plus first element of this subset of T, this is obviously in V, right? It's a vector. T is a subset of V, so it's in V. And V is equal to the span, which we just talked about. This previous statement just says that V is equal to the span of W1, W2, dot, 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 Wn. Okay. Right, and so that right there is a contradiction. We have a contradiction. Can you see the contradiction? Pause the video. Think about it for a second. What's the contradiction here? Okay. This is going to contradict our assumption of the linear independence of W1 through Wn plus 1. It's going to contradict the assumption that T, the size of T, is greater than the size of S equal to n. Because the set W1 dot 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 Wn plus 1 is not linearly independent. Why is that? Well, right here, Wn plus, this is n plus 1, Wn plus 1 is in the span of W1 through Wn. So clearly I can write this vector as a linear combination of this. So that means this vector, Wn plus 1, can't be part of a linearly independent set with these other guys, because these other guys can be combined to form it, right? So it just leads to this clear contradiction where you've got too many vectors to call it linearly independent, right? And so what that means is that this assumption was wrong, right? And so that assumption is where things went wrong. So we can go back and we can see that that's where the bad elements entered into the argument, right? And so instead, the size of T must be less than or equal to the size of S. Okay, and that's the theorem, right? So that's the idea, right? So whenever you do a theorem like this in a class, it's always like a really great idea to go, afterwards, to rewrite it and flush it out in more detail, right? A lot of times when you're in a class and you're talking it through, it can get a little conversational. Nothing wrong with that. That's how it kind of goes in school in general. But I always recommend to people to, go back, review the notes, try to fill in any of the gaps, and try to firm up any of the description of how the proof works. Okay. All right, perfect. So those are the two kind of lemmas that lead to the big theorem here. Okay, and so this is the bigger theorem. Well, they're all kind of big, and they're all in the same area, actually, but this one is, I like this one a lot, and it uses the previous two lemmas directly to makes the proof really quick and snappy. So let's let V be a vector space. Let V be a vector space, and then we've got two bases for V. So let V be a vector space, and let B1 and B2 be bases for V. Okay. Okay, so B1 and B2 presumably different, right? That's the kind of the thing you're meant to think here anyways. So we'll let B1 and B2 be bases for V such that, okay, B1 has finitely many elements. Okay, so one of these is finite. So in this case, we're saying B1 is finite. Okay, so here's kind of the wind up. So V is a vector space. B1 and B2 are two presumably different bases for V, the vector space V. And B1 is finite. We're not saying anything about B2, right? Not in the wind up anyways. But what's the conclusion? Well, then B2 is also finite. B2 is also finite, and the size of B1 is equal to the size of B2. Okay. Now, it's entirely possible that you saw this coming from a mile away, or from two theorems away, right? The first theorem has the kernel of this idea in it. The second theorem comes at it from a slightly different angle, but it also points to this as being the case. Right. What this theorem is saying is that if a vector space has a finite basis, right? If it has a finite basis with whatever n elements in it, then every basis for the vector space is finite, and they all have n elements. There's something kind of fundamental about the size of a basis, right? It can't, there's no way to write two different bases for the same vector space such that one is larger than the other. Now, there's infinite variety of bases, but all of them have to have the same size. Okay, so that size piece is really kind of a critical idea, and it leads to the definition of a dimension of a vector space, right? Okay, so that's the big theorem, right? So basically all for any finite dimensional vector space, all bases for the vector space have the same size. Let's prove this one. The proof would be really challenging if we hadn't gone through the prior two lemmas, right? But using them, we can prove this really quickly. So the proof relies heavily on the previous two theorems / lemmas. Okay, so let's prove this. So B1 and B2 are bases for V. Okay. Well, a lot of things, that implies a lot of things about B1 and B2, but in particular, one of the things it implies is that B1 spans V, and B2 is linearly independent. Right, any basis is going to be a spanning set, and it's also going to be linearly independent. We're just choosing to call out these two properties right here because we're going to set up an argument. Right, so if B1 is a basis for V, it spans V. If B2 is a basis for V, then B2 must be linearly independent. Okay, so then the previous theorem shows that basically, because we know the size of B1, right, it's finite. Well, that's one of our assumptions, right? B1 is finite. So the previous theorem shows that B2 is finite as well. And because all we're choosing to think about here is the linear independence of B, B2 must be finite in size, and it can't have more elements than B1. So B2 is less than or equal to B1 in terms of size. Okay. All right. Now that's perfect, right? So now we can kind of use the fact that now we know that B2 is also finite, and we can just flip the argument. So because the size of B2 is finite, okay, we can reverse the roles of B1 and B2. Okay, right? what does that mean? Well, because b2 is less than infinity, that means the size of b1 is less than infinity. That's not helpful. We already knew that. But the helpful piece is, the size of b1 must be less than or equal to the size of b2. Okay, so you've got this thing here, and you've got this thing here. So what are those two things together? If both of those things are true, what does that mean about the size of b1 and b2? Right, so if b2 is less than or equal to b1, the size, and if the size of b1 is less than or equal to the size of b2, what does that mean? Well, that's the conclusion that we're after. Size of b1 is equal to the size of b2. They're the same. So that tells you that all bases have to have the same number of elements. Okay? Right, so you can immediately conclude that every basis for R2 has exactly 2 elements. Every basis for R3 has exactly 3 elements. Every basis for Rn has exactly n elements, right? Because we know a basis, we know the standard basis, and so automatically any other basis, there are infinitely many to choose from, but they all have the same number of elements. Okay, very good. Okay, and so, because every basis has the same number of elements, that's kind of a foundational idea. Whenever an infinite variety of things all have something in common, you usually get a nice definition out of that, and that's where the definition of dimension comes from. Okay, so here's the other big definition, and we'll see some nice theorems with this one. So let's let V be a vector space. Let's let V be a vector space. If V has a basis containing a finite number of elements, okay, so if V has a basis containing a finite number of elements, then V is finite dimensional. Okay, V is finite dimensional. So basically, if a finite basis exists, then the vector space is finite dimensional. And in the case of a finite dimensional vector space, we can identify the dimension. So in this case, the dimension of V is the number of elements in any basis. Okay, right? So all bases have the same number of elements, and so that count, that number, is what we call the dimension of the vector space. Okay. Very cool. So now we can talk about a vector space. We can identify specific bases, but we can say something more general. We can discuss the fact that we can talk about the dimension of the vector space, which is an allusion to the fact that all bases have the same number of elements. Now, what if a vector space has no finite basis? Right? What if a vector space has no finite basis? Well, then V is infinite dimensional. Right, so let's put that in here. If V has no finite basis, then V is infinite dimensional. Okay, perfect. All right, let's see some examples. Make sure we can visualize this on demand. Right, so let's see. R3 we just talked about is 3-dimensional. No surprise there, really. But it's 3-dimensional because the standard basis. j, k has 3 elements. Right? We know that, this isn't a special, it's a special base. We call it the standard base, the most simplistic base, as you can imagine. But all bases for R3 will have 3 elements, right? If it has 4 elements, then one of them is redundant. If it has 2 elements, then it doesn't span, right? So if it's too small, it's not a spanning set. If it's too big, it's not linearly independent. How about the standard basis for M22? Right, we know what that is. It's 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. Oh, well, that's not M22, but okay. B spans M22 and is a basis. So the dimension of M22, and this is kind of the notation we frequently will use, just dim, whatever the vector space happens to be named. So the dimension of M22 is equal to 4, because a basis has 4 elements in this vector space. Okay, very good. Let's take a look at, how about this example? Let's say we have, what about P? Well, let's start with Pn. What's the dimension of Pn? Well, what does a basis for Pn look like? So Pn has a standard basis of, we'll just write B, and we said that it was 1 x squared x to the n. So how many elements are there here? 1, 2 through n plus 1. So the size of B is n plus 1. So the dimension of P sub n is n plus 1. This is an n plus 1 dimensional vector space. What about P, the vector space of all polynomials? What's the dimension of P? Well, what's a basis for P look like? If we think about the standard basis for P, what would it be? Well, it would look like this, right? It'd be 1 x squared x to the n. Are there more? Yeah, it keeps going, doesn't it? That's the problem. n plus 1. Right, so in this case, a basis for P is not finite. Right, so the size of B is infinite. Right, and so in this case, P, the dimension of P is infinite. It's an infinite dimensional vector space. Okay, and you can kind of visualize, if you think about what the elements of P look like when you rewrite them as vectors with the coefficients as elements, entries in a vector. How big is each of the vectors? But each one's infinitely large, isn't it? Right, because there are potentially infinite coefficients here for an element in P. That makes sense, right? So the vector space is infinite dimensional. Okay. All right. Let's. I'm going to go ahead and pause the video here, and I want to do a few more examples. And there's also a couple really great theorems coming up related to dimensions. So we'll have a part B for this section, and we'll get into that in a moment. So I'm going to go ahead and pause the video, and we'll see you in a moment in part B.